Hello and welcome to this PyCon 20 talk by Xilinx. My name is Patrick Lysaght and I'm a Senior Director in Xilinx Research Labs in San Jose in California. Today I'll be talking about extending the Python ecosystem to Xilinx programmable platforms using the PYNQ open source framework. And programmable platforms are user customizable systems on chip, which give you tremendous opportunity to innovate in your projects and products. So if you're interested in novel hardware and novel software capabilities in Python, we think this will be a good talk for you. We assume that everybody listening has some knowledge of Python and Linux, and that you've been exposed to Raspberry Pi and Arduino, and that you may know something about Jupyter, the Jupyter project, whether it be the Jupyter notebooks or JupyterLab. We expect that you're interested in exploiting cool hardware, and that like us, you're always keen to learn something new about Python, something new, awesome capabilities that Python enables. The talk itself is divided into 6 parts. We start with the motivation by looking briefly at the evolution of platforms. Then we talk about the opportunity, which is centered around Zynq programmable platforms from Xilinx. We also talk about the inspiration that we derive from the open source communities, in particular the Python and Jupyter communities, before introducing the PYNQ open source framework. Then we provide some demonstrations of PYNQ in action before concluding with a review of next steps. So let's begin by considering platforms. This review of platforms is not intended to be comprehensive, but to highlight some of the major trends that we've seen in the last decade. One of the biggest trends, of course, has been the Raspberry Pi. And this is typically a fairly powerful ARM microprocessor on a small development board used in embedded systems. And what's novel about this is that the microprocessor is now powerful enough to run a full desktop Linux and a fairly sizable software stack, so that we can do on-target development. And this means we don't have to do cross-compilation or cross-debug, so it's a lot easier and it's much faster. In contrast, the Arduino, which is another phenomenon, is targeted at lower-level software stacks and is deployed much closer to hardware. So it can typically be controlling sensors or reading sensors and controlling motors or actuators. And this lower level focus of the microcontrollers that are in Arduino lends them to be described as bit-banging devices. The third category we want to consider are FPGAs, and these add a new dimension. FPGAs are not von Neumann architectures. FPGA stands for Field Programmable Gate Array, meaning field programmable, as in user or customer programmable, a collection of logic gates. And what differentiates them is that the user gets to define the architecture that they want for the application that they're targeting. And this allows one to develop very parallel, very optimized, very fast solutions to problems, and also gives another degree of innovation that one can exploit. Now, whereas all of these platforms are frequently used on their own, they're also increasingly combined. And for more sophisticated and for more challenging projects, it can be very advantageous to have more than one of these platforms at your disposal. So to demonstrate an example of this trend, we see here a Raspberry Pi with an FPGA hat. So on the base card, which is the Raspberry Pi, I have my very powerful ARM microprocessors. I can run full Linux. I can have fairly sizable software stacks. And then on the top layer with the hat, I have a Xilinx FPGA where I can design a customized solution to the problem that I'm focusing on, which can give me a lot of differentiation, a lot of performance, and a lot of uniqueness that makes my project or my product stand out. So this increasing use of these different platforms together is something that you see in the higher performance, more innovative solutions. Before progressing further, I'll take a moment to refresh how FPGAs work, since not all Python programmers are equally familiar with them. This is a diagram from a book called Bebop to the Boolean Boogie, and it's a good representation conceptually of how an FPGA works. You see, essentially the FPGA is comprised of two planes, if you will. The upper plane is the configuration memory. The lower plane is the logic circuit. Now, if the upper plane is uninitialized, if it essentially contains random data, then the circuit below effectively is not configured. There's no circuit that's usable. However, if we proceed to program the configuration memory and put into it a bit stream, we can determine the circuit that's provided on the logic. And in this case, you see that with this deterministic pattern, we have a circuit configured, interconnected, and ready to go on the logic plane. So this is the beauty of FPGAs. By changing simply the bits in an SRAM memory, we can have different circuits implemented on the logic plane. Now, once upon a time, these were small circuits, but nowadays you can have millions of gates in the logic, so you can build very sophisticated circuits on FPGAs. And this just further enhances their capability. So, for example, in many computer architecture courses, students learn to build their own 3- and 5-stage RISC processors so that they can get a deeper understanding of how the processor architecture works, and their first experience of building their own processor and writing their own assembly code and higher level language code to program it. Now, we've talked about 3 types of environment: Arduinos, Raspberry Pis, and FPGAs. But imagine if we could have the best of all worlds. Imagine if we could combine all of these devices into one system on chip. So this is what we're depicting on the left here. The diagram shows Arduino, Raspberry Pi, and Xilinx FPGA inside one device. In addition to these, there are programmable inputs and outputs, and there are high-speed connections both between the subsystems and also to the I/O. Now, this is what system-on-chip integration gives us, and in fact, this capability is available today with Zynq programmable platforms from Xilinx. These Zynq devices integrate ARM microprocessors, Xilinx FPGAs, high-speed programmable I/O, as many soft microcontrollers are needed by the application, and finally fast interconnection both between the components and the inputs and the outputs. So we call this product at Xilinx the Zynq 7000 series. Now, it's not the only Zynq series we have. There are bigger brothers to this family, the Zynq UltraScale Plus, but for simplicity in this talk, we'll focus on Zynq itself. To underline the advantage of Zynq programmable platforms in a slightly different way, this comparison table shows how the Zynq programmable platform, in essence, has all the features of the Raspberry Pi, along with those of the Arduino, and integrated FPGA capability as well. And of course, because it's a system on chip and everything is integrated into a single device, you have all the additional benefits that that brings, such as lower power, lower footprint, etc. Zynq then has been very successful to date in the marketplace, and it's used in a range of very innovative products. So products like ADAS in automotive, driver assistance systems, products like process control, particularly where precision is required, high performance drones, vision processing and AI applications coupled with video, medical instrumentation, unique instrumentation, and a very exciting one, remote robotic surgery. So looking at these and summarizing them here, hardware acceleration of algorithms such as ANNs for video processing, precision robotics. You can imagine if you were doing remote robotic surgery that you don't want to use an Arduino because you might have a little bit of jitter. And you want instead to have dedicated circuits making sure that the stitching or the other surgical processes are happening precisely as you would intend them to. Real-time high-resolution video processing is another major area. novel instrumentation, and then lots of spin-offs and research groups use FPGAs because it allows them to prototype completely novel designs without having to incur the expense of making their own chips. And then FPGAs are extremely widely used in teaching, and Zynq in particular enables a whole range of topics to be taught in a single device. So you can teach logic design, computer architecture, signal processing, digital control, and of course they're tremendous for capstone projects as well. As more embedded applications transition into edge applications, there is an increasing amount of machine learning and artificial intelligence being deployed in edge devices. There are also lots more Python developers and data scientists than there are hardware and embedded software engineers. Many of these data scientists and Python developers could benefit from programmable platforms, but most are unfamiliar with the technology. The first goal of the PYNQ framework is to make state-of-the-art programmable platforms accessible to more people who could use the technology to their advantage, especially in applications such as edge devices. We also want to create a methodology for hardware designers to be more productive by using Python. And we want to make it easier for these hardware designers to share their designs with more people. In this way, we hope to remove some of the artificial barriers or layers between the different stakeholders. And we want to encourage a more agile environment by opening up new channels between all the stakeholders so that everyone can interact directly and improve their designs through earlier feedback. When designing PYNQ, we looked to the open source community for inspiration. For example, we borrowed some important ideas and best practices from Python, which we describe next. One of the biggest trends of the last decade in the open source community has been the rising popularity of the Python language. And this is primarily driven by its use in data science and artificial intelligence and machine learning communities, but also its widespread use in academia. A second trend is the use of Python for embedded or edge systems. Now, as more embedded systems get connected to the cloud in the era of the Internet of Things, we refer to those systems as edge systems. And this table, which was produced in July of 2018 by the IEEE, the Institute of Electronic and Electrical Engineers, this was the first time that they noted that Python was listed as an embedded language. Now, embedded languages typically are C and C++. These are the languages that have dominated embedded systems for decades. So this was a significant acknowledgement that Python was beginning to be used in embedded and edge systems. And it reflects the influence of the Raspberry Pi and also the additional intelligence required in edge systems which were connecting back to the cloud. There are considerable benefits to using Python in edge and embedded systems. There are millions of Python developers. It's estimated that as many as 8 million Python developers are currently active in the world. You were able to do on-target development. This, as we noted earlier, means that you're not obliged to do cross-compilation and cross-debug as you would be for C and C++, and that makes the design flow simpler and more productive. The result is more rapid iteration cycles. Python has an enormous ecosystem and a very active community. Python interoperates very effectively with C and C++. It would need to in order to coexist with them in embedded systems. And it gives us the benefit of an agile hardware and software co-design flow. And finally, there's a lot of portable code that can be reused between the desktop and the embedded and edge systems. And this results from the fact that Python executes on a virtual machine. Such is the strength of the Python community and the third-party ecosystem that Brett Cannon, one of the Python core developers, famously said, I came for the language, but I stayed for the community. And to quantify that, a study from last year showed that amongst new packages and active packages and new releases and new authors, between the years 2006 and 2018 on the Python package index, there was a compound annual growth in each of these categories that was approximately 40% or more. So in addition to the standard library that Python comes with, there are in excess of 250,000 packages on the Python package index PyPI. So you can truly say that the average Python developer stands on the shoulders of a big community, a big Python community, much the same way that Isaac Newton said, "I see further because I stand on the shoulders of giants." But one of the interesting things about a lot of these Python packages is they're not actually written in Python. Many of them are written in other languages, such as C, C++, Java, and Fortran. And that's extremely notable. One of the key strengths of Python is how well and how often it interfaces with code written in other languages. This is not altogether surprising, since we're talking about CPython, the most popular version of Python, which of course is written in C, but it's an important advantage nonetheless. We see examples of Python being used with other languages in both the standard library and in many of the packages on PyPI.org. Usually, Python invokes code written in other languages for two reasons. The first is to reuse other code by just wrapping it in Pythonic APIs, and the second is to speed up sections of Python code whose performance needs to be improved, often by using precompiled C code. For example, it's been estimated that only 17% of the scientific Python package SciPy is actually written in Python. When sharing data between programs, especially for performance reasons, it's important to avoid unnecessary copying. Python relies on its buffer protocol and NumPy's ND arrays to exchange data efficiently. These are ideas we have borrowed and reused in the design of the PYNQ framework. One of the most exciting Python projects of the last decade is Project Jupyter. As we'll see in the next slides, the PYNQ architecture uses Jupyter extensively. IPython is short for Interactive Python, and was a project that started out to create a better REPL, a better read, evaluate, print loop for Python. However, under the influence of browser-based interfaces like those in Mathematica and SageMath, IPython morphed into IPython notebooks. And notebooks are web documents, documents that have been extended to include both the source code and the results of running that code, along with all the other rich media supported by modern browsers. A key motivation behind the design was to counter the lack of reproducibility in scientific papers by providing a new kind of executable and hence reproducible document. IPython notebooks proved to be a huge success and were adopted by many other programming languages, so that the name was changed from IPython to Jupyter, which is a contraction of Julia, Python, and R, which are three programming languages. Jupyter notebooks have become the default engine of data science and machine learning and artificial intelligence, and approximately 7 million notebooks are estimated to be on GitHub currently, with usage growing exponentially. And the technology is taught to hundreds of thousands of college students each year. That said, many developers really liked Jupyter notebooks, but they also wanted more of the tools that they were familiar with from their regular integrated development environments, their IDEs. And this has prompted the creation of JupyterLab. JupyterLab is a next-generation browser-based IDE. It was developed collaboratively by academia and industry. And one of the keys to JupyterLab's success was the open source libraries that were created to enable a single browser window to contain multiple interactive resizable sub-windows or panes. So if we look at the graphic on the left-hand side, we see that the single browser window has multiple sub-windows which contain notebooks, code editors, shell terminals, and graphical visualizations of data. JupyterLab is designed from the ground up to be extensible. Each window is just an instance of a plugin, and no plugin has more privileges than any other plugin. So now developers can have notebooks alongside more familiar IDE tools, making the overall value proposition much more compelling. The real genius of Jupyter lies in its system architecture, which consists of a client, server, and language kernel arrangement as shown in the diagram. The interfaces between the blocks are well defined and based on open standards, and because it uses a browser interface, it doesn't need to support lots of different windowing systems. Instead, by using the browser, it benefits from what is probably the world's most open, advanced, and widely used computer interface. Jupyter's modular, decoupled architecture actually encourages experimentation and alternative implementations. For example, its kernel wrapper interface makes it easy to plug in new language kernels, and today as many as 100 languages are supported, including quite recently a new C++ kernel and wrapper. The Jupyter project was awarded the 2017 Association of Computer Machinery Software System Award, which is something like the Nobel Prize of software systems. Former winners have included Unix, TCP/IP, Java, and Eclipse, so it's an exceptionally good company. This prompted us to ask, what if we could run Jupyter on programmable platforms and make it an integral part of the architecture of the PYNQ framework? Consumer and professional products have been using internal web servers for many years, mostly to host embedded configuration portals. Network routers and laser printers are good examples of devices which can be configured via these internal web servers. In contrast, JupyterLab typically runs on desktop or server class machines. The idea here is to host the web server and language kernel of a JupyterLab IDE directly on the programmable platform. We can then develop on the target from a browser from any networked computer. The board shown here is the PYNQ Z2, which is a low-cost development board created especially for the PYNQ project. The PYNQ Z2 features a Zynq programmable platform, which is what hosts the Jupyter IDE. And of course, as you can see, we designed a pink colored board for the PYNQ framework to make it a little bit more welcoming and fun. This slide shows the PYNQ system architecture running on a Zynq programmable platform. We run the JupyterLab stack and the IPython kernel under Linux on the embedded ARM processors. Then we create overlay circuits on the programmable logic. Overlays are essentially highly parameterizable designs on the FPGA and are conceptually similar to software libraries. Next, we create C drivers for the overlays and wrap them in Python APIs. We call this new kind of package a hybrid package because it contains both hardware and software design elements. The hybrid package itself can be accessed from the IPython kernel in the same way as any other Python package. Note that all the browsers are hosted on external machines connected over the network. This partitioning also has the advantage of offloading any graphics rendering to the more powerful networked computers. The architecture allows software development to be done directly on the target thanks to the PYNQ framework, and no special software needs to be installed on the client machines. A modern browser is all that's required. Now it's time to see PYNQ in action. For this demonstration, we have a PYNQ Z2 board with a Zynq programmable platform connected over a network to a client with a browser interface. In this screencast, we start by accessing the PYNQ Z2 board over the network from our browser. The board responds by launching the JupyterLab page. This is exactly the same landing page that we would see if we were running JupyterLab on a desktop. For this demo, we're going to select a folder in the file browser, which contains a notebook for a machine learning classifier that we would like to open. We can scroll through the notebook and inspect its output just as we would on a desktop machine. Next, we open the Linux shell and cat the CPU info to confirm that we're indeed running on an ARM embedded microprocessor and a Xilinx Zynq device. Then we can execute a tree command to inspect some of the files on the target system. Leaving the terminal shell, we can go to the online help for matplotlib and find a radar plot that we might want to use. We can now download the example notebook and Python script to our external host, which is a PC in this case, and we can confirm that we have the new notebook and script. We can simply drag and drop the downloaded files into the PYNQ programmable platform and reopen them on the target to verify that we have both the notebook and script versions of the radar plot libraries. Finally, we can re-execute the Python code on the target without having to write a single line of extra code. So as you can see, the JupyterLab IDE works extremely well on Zynq programmable platforms, and a Python developer who already knows JupyterLab could begin working on Zynq immediately. Let's look next at the PYNQ framework in greater detail. GitHub is an excellent repository for Jupyter notebooks because it displays the rendered notebooks, which is very helpful. Here we can see 4 very different examples of hybrid packages. Recall that as part of our PYNQ framework, we extended Python packages to include this new kind of package, one that can contain both hardware and software design elements. So on the far left, the first example is a hardware-accelerated quantized neural network. Beside it is a motor control example implemented in hardware. This is the Park-Clark motor control algorithm. The third example is part of a bigger deep learning library. It's a hardware-accelerated image resizer used to pre-process images for training and inference. And the final example is an OpenCV filter also implemented in hardware. We're going to look more closely at the image resizer in just a moment. But first we would have to clone the repo to our PYNQ Z2 development board. And we can do this with just a single pip install command. And this will bring down the design, both the hardware and software elements, onto our target development board. In this slide, we look in more detail at what happens when we start to use the Resizer package that we just downloaded from GitHub. We begin with JupyterLab running on the ARM microprocessor, as we saw in the earlier demo. Now, note that at this point, the programmable logic is unconfigured. So we begin by opening the notebook for the Resizer. And then we proceed to create an instance of the overlay class parameterized with the Resizer bitstream that we want to load into the programmable logic. Once this is done, we now have the hardware design in the FPGA. And of course, we can run the notebook and have it control both software and hardware. There are, of course, more details, but these are the main concepts and are all that a Python developer or data scientist needs to know to start using hybrid packages on programmable platforms. In this slide, we show 2 sections of the image Resizer notebook. On the left-hand side is the section of the notebook that shows image resizing done purely in software, while on the right-hand side, the section of the notebook there shows that hardware-accelerated resizing. Both sections show the initial image and the image after it has been resized. The software-only resizer uses the well-known Python image library, PIL. In the right-hand section, we can see a block diagram of the programmable platform design. The hardware consists primarily of an image resizer block, some buffers, and a DMA unit, a direct memory access unit, to move data efficiently between DRAM and the programmable logic. In our second demonstration, we will show the image resizer executing first as a pure Python program and then executing with hardware acceleration enabled on the programmable platform and compare the results. In this screencast, we will download, install, and then run the image resizer. We start by checking that the design is not already downloaded. Then we open a new browser window and go to the PYNQ GitHub repo, which contains the image resizer. There we get the pip install command, which we can run in our terminal to download the hybrid package to the PYNQ board. Note we're using exactly the same hardware configuration as we did in the first demo, and we've shortened the download to save time. We proceed to open the folder and extract the Jupyter notebook. And we see the block diagram of the hardware accelerated design, which we discussed earlier, albeit in more detail. This level of detail is purely optional and is not required to use the accelerator. Here we can see that the notebook cells are unexecuted, so we select Run All Cells. And as soon as we do that, we see that the activity status indicator goes busy, indicating processing. Now we can see the results of the resizing. First we see the software resizing, and then we see resizing in hardware. You can see the results are identical. In this case, we can use TimeIt to measure the amount of time that it took the resizer in hardware, and that was approximately 4 milliseconds, which for this relatively trivial example is a speed up of approximately 3 to 4 times relative to its software equivalent. Before we look at next steps, let's zoom out for a moment to summarize what PYNQ enables. PYNQ is an open source framework that consists of both software and hardware components and builds on Python, JupyterLab, NumPy, and many other Python libraries. It can be run on a range of different boards, including low-cost development boards such as the PYNQ Z2 shown here. But we should note that PYNQ itself is not a board, it's the open source framework. PYNQ also introduces new hybrid packaging, a Pythonic way to manage designs that have both hardware and software elements. PYNQ also encourages more agile development by removing unnecessary barriers to collaboration between developers with different expertise. It allows data scientists to communicate directly with hardware and embedded software engineers and to interact with them on the same platform. PYNQ also extends the Python ecosystem by making the benefits of programmable platforms available to many more Python developers. In this, the final part of the talk, let's look at next steps and in particular, how you can get started with PYNQ. To learn more, we recommend that you visit pynq.io, which is the main site for the PYNQ framework. We also have extensive documentation on our Read the Doc site. And of course, all of the designs, the hardware and software designs which we've shared in this talk are open source and available on our GitHub repository. We have an active community page that's hosted on Discourse, and there you can submit questions and see what is trending in the community. For a full list of supported boards, please see this section of the main landing page on the PYNQ site. While PYNQ started on Zynq devices, it's now available on a range of boards, and some of these use different types of programmable platforms. And unlike the PYNQ Z2 board, which we showed you earlier, not all of our supported boards are pink in color. On this slide, we're showing a snapshot from our community webpage. It features a wide range of exciting and novel projects from all over the world, and we encourage you to check them out. One thing we've not talked about until now is how to design FPGA circuits. This was a conscious decision since the focus of this talk is not logic design. One thing to note, however, is that in PYNQ, we are not synthesizing circuits from Python. All the FPGA designs that we showed you have been created using Xilinx Vivado tools. And if you'd like to learn more about designing with programmable platforms and FPGAs, Xilinx makes these Vivado design tools available free of charge for the Zynq devices on the PYNQ C2 board, and the link here gives you access to download the software. There are also many good resources out there, including courses from Udemy, which can help you to understand what you need to do to be a successful logic designer. Here are some links to very useful PYNQ resources. There's the PYNQ main page, the Read the Docs page, the GitHub site, and also where you can go to buy a PYNQ Z2 board. To summarize, we've seen how the popularity of Python in embedded and edge systems continues to increase. We've shown how Zynq programmable platforms enable all the benefits of microprocessors, microcontrollers, FPGAs, and more besides in single systems on chip devices. We've shared how the open source PYNQ framework makes programmable platforms accessible to Python developers with minimal hardware experience. We've also seen how PYNQ makes hardware designers more productive and enables them to share their designs with a much larger Python community. Finally, PYNQ is for everyone. We invite you to explore it, and we look forward to you becoming contributors to the PYNQ community in the future. Thank you for sharing your time with us today. I hope that you found the discussion of the PYNQ framework interesting and valuable to you. On behalf of all my colleagues at Xilinx, I hope that you and your loved ones stay safe and healthy and happy in these very challenging times.